Hello, and welcome to our video on inner products. We'll start out with the finite dimensional example. Let's talk about the dot product on Cn or on Rn. So we'll take vectors x, which will have entries x1 through xn, and y, which will have entries y1 through yn, and they'll be n tuples of real or complex numbers. And then we'll put x dot y to be the following quantity: the sum from k equals 1 to n of xk times the complex conjugate of yk. And you will note that in this definition of the dot product, the conjugate goes, shall I say, on the right. The dot product considers x dot y is on the right entries get conjugated. Sometimes this is different in physics or other disciplines. I'm a mathematician, so this is our dot product. Let's look at some properties of this dot product. First, x dot y is always a complex number. Well, that's, I think, pretty obvious because you have the sum of a bunch of complex numbers. That's what the dot product is. It's the sum of products of complex numbers, so it's also complex. The dot product is linear in two senses. First, say I take alpha times x dot y, where alpha is some complex scalar and x and y are vectors. By definition, this is the sum from k equals 1 to n of alpha times xk times yk conjugate. The alpha doesn't depend on k, so I'll pull that out of the sum. This is alpha times the sum from k equals 1 to n of xk times yk conjugate. This is alpha times the quantity x dot y. And if I take x plus y dot z, where now x, y, and z are three vectors in Cn, and x plus y, the sum, is also a vector in Cn, so x plus y dot z is going to be the sum from k equals 1 to n of the quantity xk plus yk times the conjugate of zk. I'll distribute inside the sum. This is the sum from k equals 1 to n, xk zk bar plus yk zk bar. I'll split up the sum. This is sum k equals 1 to n, xk zk bar plus sum k equals 1 to n, yk zk bar. And I look at those two sums. This is x dot z plus y dot z. So I have a linearity both in terms of scalar multiplication and in terms of addition if I'm doing scalar multiplication or addition in the first component of the dot product. I also have linearity in the second component in the sense that x dot y plus z is equal to x dot y plus x dot z. However, if I do x dot alpha y, I get back alpha bar times x dot y. Those are easy calculations along the lines of the above. The important thing to remember is that linearity works the way you expect it to in the first component or first slot of the dot product, and then you have this sort of conjugate linearity, x dot alpha y equals alpha bar times x dot y in the second slot. We also have a so-called Hermitian property of the dot product. Say I look at y dot x for a change instead of x dot y. Then this is the sum from k equals 1 to n of yk times xk bar. I'm a mathematician, so the bar goes on the second component. Let's rewrite this a little. This is the sum from k equals 1 to n of the complex conjugate of y times x. So I have two bars now, and I've pulled the one bar on the xk bar up to the top. Linearity of complex conjugates says that this is the complex conjugate of the whole sum, k equals 1 to n, of yk bar times xk. And that is just the conjugate of the dot product of x and y, x dot y bar. Next, let's look at x dot x. What happens when I take the dot product of the same vector with itself? This is the sum from k equals 1 to n of xk times xk bar. Xk times xk bar, that's the modulus of xk squared. So now I have the sum from k equals 1 to n of the modulus of xk squared. And that, of course, is non-negative. In fact, x dot x, we see, is the 2 norm of x squared, where we met the 2 norm of a vector in Cn in a previous video. And so here's what we see. X dot x equals norm of x squared. Suppose that's equal to 0. That happens if and only if x is equal to 0. So what do I see? X dot x equals 0 if and only if x itself is equal to 0. All these properties can be lifted into a much more abstract definition, which we'll now use in a variety of contexts. So in general, an inner product on a complex vector space X is a map from the Cartesian product x cross x into the complex plane with a bunch of properties. And let me remind you that in our notation, x times x, the Cartesian product of x, is all ordered pairs whose entries are from x. So the inner product takes in an ordered pair, both of whose entries come from the same vector space, and it gives you back a complex number. And it satisfies the following properties. First, linearity. The inner product of f plus g in the first slot with h in the second slot is the inner product of f and h plus the inner product of g and h. And the inner product of alpha f in the first slot and g in the second slot is alpha times the inner product of f and g for any scalar alpha. We have the Hermitian property. The inner product of f and g is the complex conjugate of the inner product of g with f. So if you want to flip the order of vectors in the inner product, you have to take the complex conjugate. Positivity, the inner product of f with f is always non-negative. So the inner product of the same vector with itself is always a non-negative real number. And the so-called definiteness property, that the inner product of f against f is equal to 0 if and only if f equals 0. And if you have properties 1, 2, and 3 holding, the linearity, the Hermitian property, the positivity, but not necessarily the definiteness, we will call the inner product semi-definite, sort of along the lines of how we had semi-norms in a previous video. Some other useful properties to remember are linearity in the second slot, sort of. Inner product of f with g plus h in the second slot is inner product of f and g plus the inner product of f and h. And you have this sort of conjugate linearity in the second slot. The inner product of f with alpha g in the second slot is alpha bar times the inner product of f with g. Let's do an example. Set x to be equal to the continuous functions on the interval a to b into the complex plane, and let's give x the L2 inner product. So the L2 inner product of f with g is the integral from a to b of f of x times the complex conjugate of g of x. Again, I'm a mathematician, so the second vector, the second slot of the inner product, g, is getting the complex conjugate. Then it turns out that this map is an inner product on the continuous functions from a to b into the complex plane. You might say it's strange that we're calling it the L2 inner product, even though it's on the space of continuous functions. This is just a matter of notation, just like the L2 norm. And all the properties are pretty straightforward to check, and indeed you will do them in an exercise, except maybe the positivity property. Namely, we want to say if we have the inner product of f and f with respect to L2, what is that? That's the integral from a to b of f of x times the complex conjugate of f of x. That's the integral from a to b of the modulus of f of x squared. That's also the L2 norm of f, as we met in a previous video. And we know that if that L2 norm is equal to 0, equivalently, if the L2 inner product of f with f is equal to 0, that only happens when f is equal to 0, which is to say when f of x equals 0 for all x. And this is because f is a continuous function on a to b. So we definitely retain all the properties of the inner product for the L2 inner product on the continuous functions. If, however, we work on the larger space of Riemann integrable functions on a to b, then this map is only a semi-definite inner product because the L2 norm is only a semi-norm on the space of Riemann integrable functions.